Hello there. Hello, everybody. Um, my name is Sywula. I'm here today with Jasmine, my colleague. Both work at Python, and it is a pleasure to be here. We want to present a presentation about um, machine learning and networking. So this presentation is going to be about tuning the performance of Nginx system, and well, this is a networking conference, so you're probably very well aware of a whole bunch of different optimizations, how to optimize Nginx on many different layers. But our goal, our focus here is we're focusing on the operating system, on the Linux operating system mostly. So we're not going to talk that much about Nginx parameters themselves or other layers. So operating system is our focus, and yeah, we're going to add the machine learning on top of that. Let's see how that goes. So yeah, I'll walk you through our like a little test bench, our setup with Nginx proxy. It's going to be Nginx reverse proxy. We'll talk briefly about existing methods of tuning, how this is approached right now, and then we're gonna add the machine learning component to it and see what we can do with that. And then later, Jasmine will present the actual experiment we run with turn yourself. Sure. 1, 2, 3. All right. So Jasmine will present the actual experiment we run with. It's a very specific experiment with 16 parameters, and then we'll go through the future auto tuning. All right. So this is our test bench. This is our setup that we've been working on, and it's a little something is, and there are a few interesting things about this setup. So let me explain. So I mean, on the right hand side, you can see there's some backend servers serving the traffic. It can be a variety of different types of traffic. And in the middle, we have Nginx reverse proxy. And then on the left hand side, we have clients. And what is important about this is to notice that there's different clients. They can be mobile clients, portable. They can be on wireless networks, 3G, 4G, but they can also be wired clients. They can be, clients on the fiber connection. They can be desktop servers, like anything and everything. So that's that part. I'm kind of putting a little bit of attention. That part makes a interesting difference because, well, I'll get through that. But so just keep that in mind that there's so many different varieties of clients. So how do you approach tuning today? Well, there's always this guy at the company who knows the best set of parameters, to put on the server, that the server just works well. And if you do that, the latency is going to be perfect. The performance is going to be great. So that's how we do it, right? We do the research, look online, discuss with other people, at mailing lists, you name it. We do benchmarks, we test it, and that's kind of the approach. It's very structured. And well, we kind of do the same, right? We've been doing the same, and it works. But we want to explore how far we can take machine learning in this type of scenarios, because there has not been that much work in this area. Like we all know how much machine learning is utilized in different applications today and how well it can do for certain things, but there isn't that much out there for machine learning in administration of the system. So that's what we're doing. And another thing I want to mention, those existing methods of tuning, you'll find out your best set of parameters, you're going to put it on the machine, and it's just going to stay there forever. It's called static, right? Those parameters are static. So now when things change, uh, your tuning is not really reactive. You can't change that tuning because you just deploy that one tuning and it's there. So it's very static, and it's also not scalable for scenarios like we just showed with the reverse proxy. So, and okay, well, so when you tune the system, right, as engineers, obviously we have to realize what the goals are of the tuning. Is it the low latency, high throughput? Mostly it's going to be around those, right? Although sometimes you may be willing, oh, we have this particular corner case where we're focusing on changing the power consumption, for example, right? Or changing some other parameters. So there's different types of tunings, but that's how we start. We need to realize and define really well what is the goal of our tuning. And all right, so once we understand what the goal is, then what are the knobs that we can change? What are the tunables, the things that are to be configured? So there are four major areas, and those are memory management, CPU scheduling, networking, and I/O scheduling. And this is if you can go back. This is this can be really deep. So there are just so many parameters and things to be configured. Uh, some companies deploy custom CPU schedulers because they add so much value. Um, custom memory management scenarios, etc. So those can be very, very big areas to play with. Yeah, so CPU scheduling, one of the first ones. Obviously, the scheduling algorithm, and as I said, sometimes it makes so much value to even come up with a custom one that's only working for you or for your company. We want to look into changing the parameters of the scheduler because those schedulers are usually configurable. And yeah, NUMA, that's a very interesting topic. Basically, it makes a lot of value if you can just not have NUMA. If you want to really get the best inch of performance, if you really want to get the best performance, but that's not always the case. Many systems do have NUMA, and they can also be tuned for great performance. There is some interesting work in scheduling in NUMA environments, in scheduling the workloads and scheduling the interrupts. The part of the NUMA problem, well, what the problem with NUMA maybe is if your workload is running on a CPU that's far away from the memory, so there is the memory latency. So that's kind of the problem number one, and it's nice to be able to avoid it. TCP buffers, that's obviously one of the basic configurables. How many, what size, the values for all of those parameters need to be chosen specifically. And memory swapping, okay, that's another one. Again, it's kind of easier if you can just not deal with it and not use memory swapping at all, because again, that's going to help you to achieve the best possible performance. But that's not always the case in the environment that you may be dealing in. And sometimes it's just the memory swapping is on and you have to have it. And also, you may have other reasons to keep it on. There are some interesting projects in when it comes to memory swapping. The community is working hard on that. There is a project called Damon. It's currently upstreamed already in kernel, and we've been using Damon in some capacity. There's another project from Meta. It's called TMO. Also approaches swapping in a very interesting way. So not only you can configure swapping on the operating system level, but you can also add some extra logic on top of it. So this CTL is over 1,000 parameters, and I'm just gonna say it again. Many of you probably have your own best configuration that you just set this flag to that, set this value to this, and then it's gonna fly. But um, we just wanna see what happens if you just start playing with those parameters and changing them. So yeah, that's the most important question. Can machine learning algorithm determine the best configuration for all of those operating system parameters? And the follow-up question is, can those parameters be adjusted dynamically? Because as I showed you the picture of the proxy, um, you can come up with one configuration today for one client, but what happens when later another client comes that needs different configuration? So being able to change those parameters dynamically, that's a lot of value there. Jasmine?
Okay, thank you, Chris, for having this demo. I will take over it from here. I'm going to talk about the machine learning tuning attempts that we have made. Let's first start with the experiment design. And of course, we need to be very specific on what kind of goals that we want to optimize over with. And here, it is the HTTP latency. And next, we want to know what types of parameters to tune. So ideally, we want the AI to take over everything, including selecting the best parameters out of all the 1,006 control parameters. But that's not scalable, especially for our first attempt at a POC. So with the help of my colleagues in the domain, we have selected 16 control parameters from the 4 domains that Chris had previously mentioned. And those domains, again, they are the memory management, the CPU scheduler, networking, and the block I/O. So we have put a list of all of those 16 for your reference here. So the next one is talking about our recipe on what types of the machine learning optimizations that it takes over with. Um, so here you can see there is a chart on your right side. Basically, we start with the initial set of observed values. We are trying to build a field for people to do the treasure hunt. And then we create a surrogate function. Basically, it's like we don't know what exactly the field looks like, but we have an estimate. We have a very rough idea of a field map. And third step is we will design the acquisition function. It's more like a feedback. You take a guess. It will tell you how much you are closer to the goal. And with those steps, we are trying to pick the highest point, making it a maximal problem here. And of course, our goal is trying to find the best values there. So those are for the one iteration loop, and we want to repeat the steps 1 through 5 until we are quite satisfied with what we are finding. Okay, so with those prepared, we want to launch a benchmark. The tool that we use is the WRK. We have listed instructions here for you if you want to try it out. So for each batch, we run the tool for 30 seconds, and then we pick the P99 value to represent the results from this whole batch. So then we also want to run 30 batches, so we get 30 P99 values in the end. And then finally, the metrics formula is listed here. So we use the concept from the statistical world with the mean plus the alpha times the standard deviations. So after we have run some batches of experiments, we want to have a look at our results. There are 2 ways to look at it. So imagine you have get the results back, which a set of numbers, but the numbers is not always consistent due to the randomness of this world, right? Um, then that's why we also have to look at it from the picture side, that we got the distribution plots, as you can see on the right. So on both the left one is the average value, while the P99 value is on the right. And you can see there are three colors of different mountains. The blue one is the default value, meaning if we just use the default values for all of those 16 parameters and we get a collection of data back and then we plot them, it will look like that in this whole axis world. And then the orange one is actually the first round of tuning. Um, as you can see, it's actually not better than the default one, as the mountain is shifting to the right. So this tells us we cannot always promise you that all the tunings will return the best result. But the good thing is we can keep the best one from multiple tunings. So the green one on the left side is another round of tuning, which actually gives a better result than the default one. Okay, and for this graph, this is the experiment result to check quantitatively. We are going to examine them from both the latency and also the time it takes to get such results. So the first one is the manual testing. So here, I asked one of my expert colleagues to spend 30 minutes to use his own domain knowledge and intuition to get a latency as good as possible or as small as possible. So it took him 30 minutes, and the best result is 2.66 ms. He used that as the baseline. So, and from the lines 2 to 6, those are the tuning performance of the auto tuning, and especially with the Bayesian optimization as our algorithm choice here. So on the third line, actually the third column, you can see we use different types of the setups for the machine learning algorithm itself, which includes different acquisition functions. And whether we are going to introduce the prior knowledge or not, and also some tricks on handling the integer nature of the parameters better. So the conclusion is the best performance comes from the last row, which is using the acquisition function and also utilize the integer handling tricks. And that we get the latency. The minimum one is 2.34. That's a 12% improvement over the manual testing baseline. So for your reference, I have take the exact parameter values of the optimization results in the last slide. Oh, hello? Okay. How does it sound, everyone? Okay, great. So if you are interested, you can check the last slide at the end. So just to mention, the tuning, it takes about 17 to 20 minutes, which about 40% improvement over the manual tuning time. Okay. To help you better understand how the whole tuning process takes, I have taken some screenshots and make an animation. About 40 seconds. Let's take a look. So for this plot, the x-axis is p99 percentile, the p-value, and the y-axis is the density coming from the data distributions. So for the blue one, it's the best manual baseline we have there for us to start with. And the gray line is the current tuning performance. And the green one is the best Bayesian result that we want to keep in the end. So as you can see, it is doing the trial and errors, shifting the distribution is shifting to the left and the right. But in the end, we end up with something better to the left of the baseline one. Okay. So that's a brief review of the results that we have. Here, I also want to share with you some fine-tuning tricks that we have deployed from the machine learning perspective. The first one is the prior knowledge from the kernel SMEs is useful. So, because when I began at the very start, we have 16 parameters, and each of the parameters has a wide range set. It's quite difficult for the Bayesian to converge to. So we took some input from the subject matters to say, okay, what do you suggest? What's the mean to the max range? And what kind of steps should the tuning take to do the tuning better? So for example, for the range of schedule latency NS, we have a range from this small 12 to 24 times the multitude instead of using all the values of the 12th one. And we also tried different acquisition function settings. So we have here are three of them: the upper bound, confidence bound, expected improvement, and probability of improvement. But those just beginnings. Maybe in future they could come with better machine learning parameters values. And we also have some observations that I want to share. So the first one, of course, the manual tuning may not always give the fully optimal performance. And the second one, if we have endless time, we want to get the best values, but we still have time constraint. The more parameters that we want to use, the more time it takes to tune. So we want to have this in our consideration and balance the time and the performance. And the third one is the prior knowledge, the inputs, it will contribute to better performance in a shorter time. And the fourth one is comparing the dynamic tuning versus the static one-time tuning. So the benefits of the static tuning is it gives you a lower computation cost. It happens when you have a pretty stable environment where the end goal does not always change that much. We also have an alternative of the dynamic tuning. Its benefits, especially when the environment variables always keep changing. But of course, that gives us a higher cost of the computation thing. Okay, so that's for the machine learning results and findings. We will also have some future work.
So thank you, Jasmine. Jasmine presented this really exciting experiment. There is a lot more we currently do work on and that we're planning on working on. Obviously add more parameters that we're tuning, especially around the TCP congestion control. And the third one, that's a funny one. So when we've done the experiment and presented the results to some of our friends, they were like, hey, when you're changing the TCP buffers like this and that, there's this other flag that you have to set and you didn't do it here. I'm like, this is so good, because it's like we're running this machine learning experiment and it actually, like the machine learning part didn't do it. And my friend was able to catch it. So that's a great feedback from human beings that we can get, that we can introduce back to the algorithm to make it only better. So that's part of it, being able to work with human beings to be able to catch and see the things that actually machine learning didn't optimize. Yeah, and also another part of it, use other optimization algorithms, not only Bayesian optimization, but other ones, especially in the scenarios where we have dynamic workloads, because Bayesian optimization doesn't handle, because there's that time delay, it doesn't handle dynamic workloads so well. So this is our future work.
Questions? Oh, Mike, we're trying an experiment. You have to go to the mic. I have a question. Well,
hello. Thank you for the talk. It's exciting to hear about machine learning and performance optimization. I have a question. In your slides, you showed that you use the WRK benchmark tool to optimize and tune the performance, but do you have results on real production server? Because it's really different. the client's workload very different, and requesting index page isn't the same as requesting many pages. Obviously, you have different memory profile, scheduling profile, and also on real servers, you don't usually, I don't know your production servers, but typically you don't have only Nginx on it. You probably have monitoring system, many some agents which collect the latency and so on. So we saw, for example, a case when we had dramatic reduction on tail latency on production system just because of monitoring, because Linux scheduler treats aggressive, computational aggressive Nginx and monitoring very differently. So the point is that production environments very changing. You have different time, different workload, and during each time it's also very changing with very different profile.
Correct. So let me answer that to the best of my ability. So it's similar for us. Of course, there's a bunch of agents running on the system, monitoring agents, whatever. There is other stuff running other than just Nginx. In production, we try to approach this where we, take all of those things into account. But for this particular presentation, we just wanted to extract what's the core part. That's why we use WRK, and that's why we just focus on kind of a very simple scenario, because if we added all of those things on top of that, it would be very difficult to understand what's going on and understand what is actually improving. So we've used WRK specifically for the purposes of the experiment and the presentation, but all of those variables that you're mentioning, of course, they're important and they do affect the latency. So we take that into consideration as well.
So as the answer is that in production it still does work, and it doesn't find the optimal settings for production servers.
So when it comes to production, we don't have this particular version of the algorithm deployed right now in production. This is still work in progress. We have some other tunings kind of working, but this particular approach is currently not.
Okay.
So this is still work in progress.
Okay, thank you.
Also, to add to Chris' comment, so I think ideally we want our result to be robust enough, meaning even though the environment is fluctuating, our recommended optimization parameters can still give you a better result than the normal default ones. That's why I use the check it from the distribution perspective instead of just the mean values. So if you, by looking at the distribution hills, given the change of environment, it still delivers a stable, say, a mean and standard deviation. For that, then we can get the confidence to say, okay, here are the parameters values that we want to deploy.
Yeah, I'm sorry, my check. I'm going to have to cut. One last question here. Then we're going to extend the break. It's break time, so 5 minutes.
Oh my God. All right. So, so basically I have a question about the tool itself that you actually use to measure the delay. I'm actually just taking the delay measurement as like, end to end the one HTTP transaction and stuff like that. I'm assuming that's what you use. And when I, so that you're basically trying to optimize 99th percentile, the delay time, it seems like you're basically optimizing for a large file, large transfer in that workload. I don't know what that workload is. So basically, what I'm trying to say is, your method might actually be optimizing the system for larger object transfer, but that doesn't really mean that it's going to be a optimal, for small object proxies. So, I think you should take a very careful, measurement. What I'm trying to say is, like, from the measurement perspective, your target, right? Your objective function should be after, what's your real objective. Okay.
Correct. Okay, thank you. So in this isolated scenario, when we use WRK, we have the comfort that we kind of have control and ownership of both of the machines, so we can measure whichever way we want the latency and the delays. In the real production environments, you're talking about the customer that may be, on another continent or wherever else, and being able to measure the latency directly from the customer is not always possible. There are some ways that you can leverage. There are some tricks that you can do, but it's not always possible. So it really comes down to real world scenarios. So you take next best thing you can do. So maybe you measure from the first router or the first networking device, or so it's just that we don't always have a comfort to have all of the metrics that we would like to have.
Thank you.
Thank you very much.
Here. But a question for everybody: is the audio good in the room? Okay. Do we need to fix it, or it's good enough? Okay. Thank you.